we're talking here, and about how the technology changes so fast compared to what it used to change. And really the bottom line for engineers is that if you're fundamentally grounded in the engineering principles, you learn what you need to learn to get the job done. Okay, and that's what it's all about. At this time, I'd like to introduce Chris Washington, NI rep. He's very closely associated with Veristan, and maybe all of you don't know, but we have a package that called Inertia that marries to Veristan to do dyno testing and so on like that. So at this time, I'd like to introduce Chris Washington. He's got the keynote speech.
Thank you, Jim and Matt and Darren and the rest of Wineman. It's my honor to be here to speak, and to all of you, thank you for your time here today. I hope it will be well worth it. A little bit about myself. I joined National Instruments in 2002, and shortly after that moved up here from Austin, where I was born, to Michigan, and lived here for 3 years. Loved it. Worked with Wineman as well as many of the customers here in the northeastern part of Michigan, or eastern part of Michigan. And after spending 3 years in the field doing that, I moved back to our corporate headquarters in Austin and became the product manager for our real-time testing business area. And so one of my roles or responsibilities as a product manager is to gather feedback and use it to provide guidance for how we invest our R&D resources into tools for this specific business area for real-time test. And so as part of executing on that responsibility, I've had the opportunity to actually interact with quite a few customers from around the world and various industries. And so what I want to do today in the next 30 minutes or so is share with you guys some trends that I've seen during the last, I guess, 6 or 7 years that I've been doing this role. But maybe more interestingly, share with you guys some technologies, as Jim mentioned, some of the latest technologies that are emerging that we're seeing be used to address some of these trends that we've noticed. Okay, so this is probably not a shocker to anybody in this room, but embedded software is, I don't want to say out of control, but it is growing very rapidly. We find it in just about everything now. Here we've just got a few statistics that I pulled to give you guys maybe an idea of the amount of software that is part of these mechatronic systems such as airplanes and vehicles, but it's really not just transportation. Even our smart washing machines and our smart dryers now have upwards of 100,000 lines of code. And I start to think about debugging code I wrote in college that maybe was a couple thousand lines, and then I start to look at what's happening now in products that are being run, 10 years, day in and day out. And we've got a significant challenge as test engineers to ensure that errors in the software don't get passed on and through to the customer. And maybe what is the more sobering statistic that I came across here was that what the future is for this. All right, and so this was taken from a presentation I watched by one of the OEMs here in Michigan that was talking about the evolution of software. It's not their actual vehicles. I made the graph myself, but the evolution of embedded software in the vehicle. And you can see that moving forward, it's going to be a very, very large task to validate. Now, to add another piece to this, in The Economist publication, there was an article I read where NASA was talking about how they had commissioned a study to determine what was the maximum, the best possible quality software that could be produced using the best practices. And what they came up with was 0.1 to 1 error per 1,000 lines of code. No matter what you did, just the nature of software, of especially large applications, what was going to happen. So now if you take that factor and then you multiply it by the amount of code we're getting, as test engineers, which I know many of you in this room are, that's a significant challenge, both today, where we're at today, as you guys are full aware, and where we're headed in the future. Okay, so given all of this, this is a problem that's been around for a while, embedded software, and there's a good tactic or technique that is being used to address that called hardware-in-the-loop testing or hardware-in-the-loop simulation. And the reason this is necessary really becomes because there's a challenge when testing embedded control software. Okay, so in this particular illustration, I've got an engine control unit, but you could really replace any mechatronic system here, and the same would be true. You've got all of the complexity that is being added into the system, or most of it, is being added in this form of software here that is controlling how the mechanical system is going to operate. Okay, so then as a test engineer, you would say, okay, if a lot of the new complexity and the new errors I got to find are in this component here, I need to find a way to test that more. And then the challenge there is that you cannot test control software completely without the rest of the system that is intended to control. And that's because there's a excuse me, and that's because there's a closed loop coupling or a closed loop interaction between the software and the engine. So many of you in this room may already know this, but it's effectively your software is reading the current state of the system and making adjustments on the fly to automatically control how it operates. And so you need the system to test the software completely, but you can't always scale your test resources, your test capacity, proportionally to the amount of additional testing you need. You can't just add 20 dyno cells necessarily to scale. That doesn't scale with the other factors you're trying to balance of budget and timeline for the project. And so that's where hardware-in-the-loop testing comes in. And this is a technique that's been around really for decades, going back into the mil-aero and aerospace industries have been doing simulation with C-based models for years. But it's really been refined and optimized now by the automotive industry with their shorter, leaner development cycles. And what we do in hardware-in-the-loop testing is we replace the physical system with a real-time simulation. And that real-time simulation tricks the unit under test, the embedded control unit, into thinking that it's talking to the real world. And it does that through electrical simulation. So if you think about it, if you put yourself in the shoes of an ECU, or in the box of an ECU, and what do you know about the world around you? I mean, you've got Ohm's law and time. You know voltages, currents, loads, and then the time or the waveforms, as the transients as they change. And that's how data is communicated from the physical world through sensors and actuators into the electronic control unit, or the software world. Okay, and so hardware-in-the-loop simulation is simulating the dynamic behavior, the response of the system, and enables you now to have more repeatable testing. It'll enable you to do test scenarios that you ordinarily would not want to test. I was talking to Embraer earlier this summer, and they were talking about their Iron Bird, and the way they described it was, if you want to test how your plane is going to operate when both engines fail, that's not a test you want to do in the air, And there's many examples like that in all of these industries. And using simulation will allow you to test for those scenarios that you hope never happen, but at least to know what will happen if they did. And so hardware-in-the-loop testing has been a technique that continues to grow in its usage. And if you recall the graph I showed previously, with the exponential growth in the content of embedded software, and as it is leaking out into industries beyond auto, aero, into white goods and medical devices and growing there as well, there's a lot of investment going on in the area of hardware-in-the-loop testing. And a lot of that investment is being made by the tools providers. There's a big need there, and so it's tools providers, companies such as National Instruments, are wanting to provide the tool that everybody wants. And so there's being investments into the testing tools, but what I want to specifically talk about is there's been a lot of investment into the modeling tools. All right, so critical to doing hardware-in-the-loop simulation is you have to have what's commonly called a plant model, or a mathematical equation that can be executed deterministically in real time to simulate the response of the system to the inputs and publish those out via the outputs, the sensors, to the ECU. Okay, and so you've got to capture the dynamics to whatever degree of fidelity or accuracy is necessary to validate your particular system. And so here's a list. It's not exhaustive, but it's a fairly complete list of tools that are used, that I've run into, that are being used to create these simulations, these real-time simulations for HIL. And that really brings me to the first trend that I've been seeing in the area of physical or mechanical testing. And it's really that engineers are starting to realize that there is a lot of investment that's been made into those models, whether it be investment in your own corporation And by simply asking, you can actually find a very accurate plant model of your system that you could leverage. Or in some cases, particularly in automotive, there are modeling environments that actually provide ready-to-use models. So you don't even have to understand the mathematics and physics behind creating a model. You just need to fill in the parameters that are specific to your system, like the width of a tire, the bore of an engine, the friction of the contact of the tire with the road, and so on. And so really this first trend or technique that in the last couple of years I've started to hear more and more about use cases is really leveraging these HIL models, the models traditionally used for HIL, to improve the physical testing.